right. Hi, everyone, and welcome to the second session for today. This is, the title of today's fast pitch session is Teaching Old Systems New Tricks. My name is Victoria Chernow. I am a fellow with ARPA-E, and so in the spirit of the reboot and everything old is new again, I want to take you on a journey today through the technology timeline. So, for this particular session of talks, we're going to first start by looking at a technology or system that is about 385 million years old. That's trees and forests. And then we're going to skip ahead a couple 100 million years and look at the origins of the electric power grid, then move on to discussing powered flight, then the mass manufacture of the automobile, and then we're going to end by looking at analog computing. And so basically, we're here today to discuss the next generation of all of these technologies. So the first two talks are going to explore the transformation of existing systems. I'm going to talk to you today about trees and forests and how we can increase the carbon sequestration potential of trees and forests. I'm then going to hand it over to Dr. Kory Hedman to talk about reforming the grid in the age of renewables. The next set of talks will look at reimagining foundational technologies. Dr. Chris Atkinson is going to talk about energy and autonomous vehicles. We're then going to have Dr. Isik Kizilyalli look at power distribution in electric aviation. And then we're going to welcome Dr. Michael Haney to talk about the energy efficiency prospects of analog computing in a digital world. So, as a reminder, please engage with us. ARPA-E is always interested in hearing new energy-relevant ideas and feedback, and so I want to encourage everyone to text us questions after each of the talks. And again, please note that your messages are going to be limited to 160 characters, so please keep that in mind. And furthermore, please come talk to us after the session, and certainly during ARPA-E coffee hour and by email. So with that, I would like to start by bringing you back 385 million years to talk about trees and forests and how we can bring trees to the forefront of biotechnology and material science innovation, and really ask, what would you, could you do with wood? So I think we're all generally familiar with trees, but if we were to recast trees as an engineered system, we could talk about the leaves and foliage being a direct air capture system. So a system that allows for the uptake of atmospheric carbon dioxide via the process of photosynthesis. And so a tree trunk is not just wood, but actually a highly complex, architected, multifunctional carbon-based material. And when we look below ground, we see that tree roots are not just tree roots. In fact, they're a complex system for mass transport. And roots are surrounded by a highly complex system of fungal and microbial organisms, as well as carbon, organic, and inorganic soil. So generally, as I've mentioned before, trees have had millions of years to evolve. But if we talk about a tree as a carbon storage and capture system, it hasn't had the time to be optimized to the sequestration needs of today. So this really motivates my asking the question, how can we increase the carbon sequestration potential of trees and forests? And so acknowledging the fact that tree genetics basically give you the potential for the amount of carbon capture and storage that a tree is capable of, I want to ask, how can we reimagine biological processes to increase carbon atmospheric uptake? How can we look at strategies for allocating carbon preferentially into high-value solid wood? Can we look at genetics to improve tree growth rate? And finally, can we also look at genetics as a means of turning trees into being better able to live on non-agricultural land? Can we think about ways to have them survive in arid and degraded land, and also perhaps remediate this land? So, again, if we're going to talk about maximizing CO2 uptake and assimilation, probably the best place to start is by talking about photosynthesis, which is the basis by which plants grow. So here we have a very simplified view of the photosynthetic process that takes place in a leaf chloroplast. And so one way that we can think about maximizing photosynthetic productivity is by looking at how we can improve light capture within leaves, looking at how we can improve light interception. And so we can do this by better understanding the genetic origins of leaf distribution, shape, and size, and really optimizing them to be better able to capture light. Then moving inside the chloroplast and in looking at the photosynthetic pathways themselves, we can think about ways of perhaps extending the waveband of light available for the process of photosynthesis by incorporating cyanobacterial chlorophyll into higher order plants like trees. Then if we move over to the other side of the photosynthetic pathway, to the carbon fixation portion, we can look at methods for improving the kinetic properties of rubisco, which is the enzyme that actually enables the fixation of carbon. We can also begin to think about ways of enhancing carbon concentration around the rubisco enzyme, and also limiting the amount of CO2 that's lost due to photorespiration. And finally, I think probably the most challenging thing that we can start to attempt to attack is introducing the more efficient carbon fixation process that is C4 into trees, which are actually generally C3 plants. And so that's on the carbon uptake side of things. But the other thing that we want to tackle is, once we've actually taken in this carbon, how do we ensure that it preferentially gets turned into high-value woody biomass? And we can, again, look at strategies for doing this by understanding and helping to regulate genes that increase tree properties like tree height, tree thickness, and the dominance of the trunk versus branching, for example. But we should also be looking at strategies that can affect the biosynthesis of carbon-based polymers that comprise wood, like cellulose and lignin. And so, in some sense, all of these strategies that I've just talked about have been explored to some extent in model plant systems and in agricultural crops, but their application in trees has been certainly limited, and that's partially because trees are far more complex and slow-growing than other plants. But I really want to ask, can we begin to apply the processes that we've started to find in synthetic biology, like multi-omics and high-throughput screening, to really accelerate this process of tree engineering? Now, the other thing I want to address is this common criticism that afforestation is going to be taking up land that we could otherwise be using for agriculture. So in some sense, I think this motivates the question, how can we make more productive trees on existing land? And another thing that I think we need to do in order to address this question is look at how can we affect tree growth rate. So right here, we have a very simplistic growth rate of a tree. And so all of the previous things that we've talked about have been strategies for increasing total tree biomass. Literally, how do we bring up this curve to actually sequester more carbon? But the other thing that we really need to do is push this curve and ask, how can we use genetics to grow an oak tree at the rate of bamboo? And so recent work out of the University of Manchester has basically found two particular genes in the poplar tree species that, when overexpressed, actually led to the doubling of tree growth rate. So the next question is basically, what are corresponding genes in other species that can be similarly modified to affect changes in growth rate? And furthermore, can we begin to engineer trees that will not only grow and thrive on degraded and nutrient-depleted land, but also perhaps begin to remediate this land? So, once carbon is captured and converted into biomass, how do we ensure that it actually stays sequestered? Well, returning to this growth curve, I think it's pretty clear to see that at some point in a tree's life cycle, the amount of carbon that it can possibly uptake is going to plateau. And then eventually the tree will die and begin to degrade and re-release carbon dioxide into the atmosphere, as well as other greenhouse gases. So one way to mitigate this decay and re-release of CO2 is by better understanding the microbial and fungal degradation process and perhaps beginning to re-engineer that. Alternatively, though, what about sustainably harvesting mature trees and turning them into a long-lived carbon-rich material? So one way that we've already started using wood as a long-lived carbon material is through the use of mass timber in the construction of tall buildings. And so mass timber basically allows us to build multi-story structures that are completely made of wood, so both in the frames and in the paneling. And this is just beginning to be more accepted in the United States. We can now basically build up to 12-story buildings using mass timber. And one of the big benefits of mass timber is, without even considering the amount of carbon dioxide that's stored in the material, simply using wood for these kinds of structures will displace about 4 tons of carbon dioxide equivalent relative to the use of carbon-intensive materials like concrete and steel. But what I really also want to ask is, what are those next generation wood products that would also allow for long-lived carbon in the construction sector? So recent work has shown that there are ways to post-process your wood in order to make transparent wood, and this is a highly insulating, transparent wood materials. So can we envision in the future creating our buildings to have wood-based windows instead of glass? That would be pretty interesting. Also, work that has been recently funded by ARPA-E has found a way to post-process wood in order to create super high-strength, lightweight, densified wood. And recently, this work has been extended to show that this wood is also capable of acting as a passive daytime radiative cooling material. So again, this is really exciting work being done with wood, a relatively kind of standard material. But I really, again, want to ask, what's the next generation for wood products? So again, going full circle, the net amount of carbon sequestered in a tree is both a function of environmental interactions as well as tree genetics. And so environmental interactions are things like sustainable land management. However, tree genetics are an area that I think really requires far more research. And so, again, I want to leave the audience with this question of how can we improve biology to really maximize forest carbon sequestration? And furthermore, once that carbon is sequestered, how do we make sure that it stays stored? And so, with your help, I'd really like to ask, what are these next generation wood-based products that we should be looking at? And furthermore, how can we really achieve complete utilization of all wood-based components in case some sort of post-processing needs to occur? Sorry about that. Basically, I want to end with your input is key. I really hope that you will engage with me on talking about how we can possibly engineer trees and how we can possibly look at the next generation of novel wood-based products. So please remember to text us your questions and certainly come speak with me. Thank you so much.
Thank you, Victoria. Thank you all for being here. My name is Kory Hedman. I am a program director with ARPA-E. My talk is going to focus on how we can take innovation in the grid management space to transform challenges into opportunities. What are those challenges? Well, today we really see the intermittent resources like bulk renewables and distributed energy resources as a challenge. We want to understand how our management practices can change that. So in terms of the electric power grid, actually it's one of the most complex engineered systems to date. And in fact, as mentioned earlier today, the electric power grid was deemed to be the greatest achievement of the 20th century by the National Academy of Engineering. It's a very complex system spanning thousands of miles, millions of assets, and behind all of that, similar to the picture you see, is a complex management system. And there's that complex management system that's not getting enough attention, that we want to pour more attention towards it. As you go in the direction of revolutionizing the grid with modern resources and modern technology, you also need a modern grid management system, and that's what we're aiming for. And so one of those main goals that we have is that we want to utilize all of our resources out in the grid for grid operational reliability requirements. What do I mean by that? Well, that's not really happening today based upon the way that the management systems are designed. They're very much designed for the conventional technologies that have existed for decades. They're far less designed to operate and to leverage the resources that are coming in today, like bulk renewables and distributed energy resources. So that has to change. What also needs to change or go in that direction as well, with that utilization, we need to leverage those resources and their flexibility relative to their dependability. So what does that mean? Well, if you think about it, how can you rely upon a natural gas to provide the services that you need to make sure the lights stay on? But then ask the question, do you control the wind? No, you do not. But you can predict the wind, you can predict its capability to provide the services that you need. And so that is where we need to have a change, and we're not doing that as of yet today. And the outcome of all of this is that if you go in that direction, you will find yourself with a risk-driven grid management and operational paradigm that does not exist today. This is what my talk is about. This is what we're seeking. In terms of this next slide, this is just a quick overview of where all of our renewable portfolio standards are as of today across the United States. Now, they all vary, but there's one very thing in common across all of them. They all focus on percentage of annual energy production from renewable resources. But that is not what all the grid is about with that complex system. There's much more to it. Reliability services are required to keep the lights on. And this one simple example is just to show you an example of load following. But there are a long list of reliability requirements that are out there. And that is what makes sure that this complex system maintains an affordable amount, electricity is affordable and reliable for you. And the importance of that is you see, well, if you go back to the 2003 blackout, we had that blackout cost us about $10 billion. So there's a lot of importance on reliability. There was a previous panel today, and things that are important for electricity are affordability and reliability. But the future grid, with all of the renewable resources we're getting on the system, flexibility is going to be very important in terms of achieving that. So where do we have this issue? Well, again, the existing paradigm that we have sees these conventional resources that we've known and trusted for decades as the ones that we should rely upon to provide the reliability services that we need to keep the lights on. And instead, the renewable resources, distributed energy resources are very much instead seen as a negative externality, something that the conventional resources must compensate for. That's where we need a shift. We need to be able to understand each asset and the risk it exposes onto the system relative to its dependability. And when you do that, you create that common framework, then you can create an appropriate trade-off between the natural gas power plant providing that service versus the renewables. It's not as if the renewables cannot provide these services. It's the question again as to whether the wind will blow 6 hours from now. That is different for those renewables than the natural gas or the thermal units, and that is what our management systems are lacking. That challenge, again, exists in that complex paradigm of the operations and the management systems that back this engineered system. The power grid for the longest time has achieved great feats, but it is in that system that have these challenges. And where that comes into play is very much across this time dynamics that occur when the grid operator has to make a bet and acquire reliability services in advance of the real-time operations. They start planning weeks in advance, days, hours, minutes in advance up into the real-time operations. But as you get closer to real-time, so do you also lose the flexibility in your system. On the reverse of that, our confidence in our intermittent resources grows as we come closer to real-time. What's not happening today is that ability to, again, make that trade-off between the renewable resources providing these necessary reliability services versus the conventional thermal units. That is what we need to invoke in terms of our grid management practices today. How do we manage renewables today? This is an example from California on a day in April of this year. The green line at the top is the overall renewable energy production that they had across this 24-hour time period. Now, then spot the red curve. That is the overall imports of electricity into California across the same day. Actually, California, with its aggressive renewable portfolio standard goals, are already having trouble managing their system. This example shows that they are very much reliant on this day on their neighboring states to provide the flexibility to compensate for the renewables. It is the neighboring states that compensated by pulling back on their imports into California. So we already have a problem today, and yet we want to go further. We need to solve that. In terms of this next chart, this gives you an understanding of the monthly curtailment of wind and solar in California back to 2015. It's been increasing, and it will continue to increase as we have more and more renewable penetration. And if you look at the month of May alone of this year, you're talking about roughly enough energy to power about 250,000 homes. Okay? Why is this happening? Well, it's actually going back to that chart that I had on the challenge before on the time dynamics. When the operators have to make that bet as to what services to acquire from different resources, they sometimes will over-acquire from the conventional baseload units, and so therefore there's too much capacity already on from the conventionals, and the renewables get displaced. So we have to change that. We have to have an understanding as to how the renewables, which can provide these reliability services today, but they have that risk component to them, how can we extract those reliability services from them? Okay, so what are we asking for from ARPA-E? We need a common risk management framework for the modern grid. Again, I will say, if you want a modern grid with modern resources and technologies, you also have to have a modern management system that backs that complex engineered system. That is where we are lacking. It needs to start with quantifying the asset risk of the asset itself across the entire system. We don't do that today adequately. And by doing that, we can then again make a comparison to the fossil fuel units that we rely upon. Then you have to take on a collective basis how all those assets come together at the systems level and make sure that you maintain your system operations appropriately. So you have to hedge that system risk position associated to the collective asset risk that you have. In order to get there, you need to make sure that you're leveraging the flexibility across all assets, instead of having an operational paradigm as we have today, where certain services are pretty much segregated to a particular type of class of units that we've relied upon and trusted for decades. That needs to change. And through all of this, you will then get an operational paradigm that's valuing your asset based upon its performance. This doesn't happen adequately enough today. This would be a big game changer for renewable resources, distributed energy resources, but also something I haven't mentioned, of course, storage. Storage is the ultimate asset that provides you risk mitigation. And if you don't have a risk management paradigm, you do not value storage adequately. And so with that, I want to thank you for your time. I will be available Wednesday morning during the office hours, and you can also email me, and then I'm going to hand it over to Chris Atkinson.
Good afternoon. I'm Chris Atkinson, Program Director at ARPA-E, and I'm going to talk about energy and the new mobility. How disruptive to energy will autonomous and automated vehicles be? The future of the transportation is autonomous vehicles. This fine picture from GM in the 1950s shows the future that we have ahead of us. But actually, this is our current reality. Everything that you've heard about autonomous vehicles and their energy implications is wrong, completely wrong. Common myths about AVs and energy: all autonomous vehicles will be electric vehicles. Perhaps in some far distant future they will be all electric vehicles. But initially, at least, there'll be hybrid electric vehicles and plug-in hybrid electric vehicles, or even conventional internal combustion powered vehicles, due to the significant energy and power requirements that are required for the machine vision, the perception, the data fusion, the onboard computation, the decision making, and the automation that they require. The second myth: autonomous vehicles will reduce our total VMT. VMT being the composite vehicle miles traveled by all vehicles in the United States, for example. AVs will reduce our total VMT. To the contrary, VMT could double or treble. This could come about due to a confluence of unfortunate events. Vehicle occupancy is already staggeringly low, at about 1.2 occupants per vehicle in the United States today, in certain areas at certain times. If we have vehicles that are single occupant, or indeed if we have vehicles that have no occupancy, in other words, so-called dead miles traveled, we could double or treble VMT. And this would be especially deleterious to our energy future. AVs will ease congestion. Again, reducing the cost of travel will simply induce more travel. We know this extremely well. It's the energy rebound effect, or the Jevons effect. And in the future, we'll drive by proxy. These vehicles will be driving around at night, collecting our groceries or our dry cleaning. And this will increase VMT enormously. AVs will encourage ride sharing. You must remember the distinction between ride hailing and ride sharing. AVs encouraging ride sharing. To the contrary, if the cost per mile traveled is reduced, there'll be even less incentive for people to share rides than there is today. Why share a ride at $1 per mile when we don't share that same ride today at $2 or $3 per mile? So the potential autonomous vehicle energy implications are staggering. And because we're in Denver, Colorado today, I have to show a slide from NREL. And it shows that we could double or treble the energy usage in the future if we do not make significant improvements to the energy intensity of travel and significant reductions in vehicle miles traveled in the future. This is from the Energy Information Agency, of course, our sister agency in the DOE, and they show very much a reference case, a sort of a business as usual case, but it shows that transportation is second only to electric power in the United States in terms of its energy consumption. It will drop in the future in the reference case because vehicles are becoming more efficient over time. But as VMT increases, you can see that the transportation portion of our total energy consumed will increase. And petroleum and liquid fuels, by their projection over the foreseeable future, will remain highest, above even natural gas. Clearly, this is very problematic from ARPA-E's point of view. Making future autonomous vehicles more efficient, this we know how to do. We already know. Downsizing, downweighting, improving the efficiency of internal combustion engines, increasing levels of hybridization, increasing electrification, and then ultimately full vehicle electrification. And this considers only vehicle-related technologies and not improvements to infrastructure. It doesn't take into account regulation, policy, or incentives, for example. Purely a technical viewpoint. But we clearly would like to go from this in the upper left-hand picture, which is our dystopia today, to some sort of an autonomous vehicle, fully electrified future. And ARPA-E's Next Car program, which is 2 years completed out of 3, was designed to do exactly that, but for L1, L2, and L3 vehicles, the lower levels of vehicle automation. The idea was to use vehicle connectivity and low levels of automation and employ those techniques, including eco-routing, eco-driving, hybrid electric energy flow optimization, vehicle platooning, and other connected and L1, L2, L3 automation techniques to improve the individual energy efficiency of vehicles by 20%. Bear in mind that for any powertrain or vehicle energy technology to replace the incumbent technology, it needs to be better than or comparable to the incumbent technology in 8 specific areas: power or power density, energy efficiency, regulated emissions, total costs, including total cost of ownership, reliability, the utility of the vehicle or that particular powertrain technology, the acceptability of its fuel to the consumer, and ultimately safety. Now, a number of these are consumer acceptance requirements, and a number of these are regulation. It's a combination of the two. So beyond Next Car, what we're interested in finding out is if Next Car improves the efficiency of L1, L2, L3 vehicles, which of those technologies can be applied to fully automated vehicles, those known as L4 and L5. The safe deployment of energy efficient L4 and L5 automation is key, as this picture shows. We would like to find out what technologies can be applied to fully automated vehicles, short of full electrification, that can improve their energy efficiency. As you can see, safety is critical. We've done a remarkable job in the United States of reducing vehicle deaths per billion miles of VMT. And the last thing that we would like to see is any uptick or increase in that. So, vehicle safety, we believe, is a key enabling technology for future vehicle efficiency. What if VMT increases significantly? How do we reduce the energy consumption of the future AV vehicle fleet? And as I have said, what energy efficient automotive technologies beyond those described here remain to be developed for L4 and L5 autonomous vehicles? I would very much like to hear your input. I too will be at the coffee time with your favorite ARPA-E program director tomorrow at between 8 and 9 a.m. Please contact me. Thanks very much.
Press which one?
Just press the green.
Good afternoon. I'm Isik Kizilyalli, Program Director at ARPA-E. I'd like to take this opportunity to speak to you about electrification of commercial aviation. In particular, I'd like to talk about power distribution grid, cabling, and insulation materials on board for electrifying a long-haul, wide-body aircraft. Hence the title of my talk, 10 kilovolts at 10 kilometers, will it fly? I'd like to reduce my carbon footprint, but as much as I try, I will not be able to reduce my carbon footprint due to air travel. As a matter of fact, air travel is one of the most difficult industries to decarbonize, and it's also one of the most rapidly growing. Mechanical power required for an Airbus A380 aircraft at takeoff is about 200 megawatts of mechanical energy, mechanical power. This is utility scale power on board, equivalent to powering 20,000 homes. While cruising at altitude, the power levels required are much less, a fraction of this, but still substantial. A state-of-the-art power distribution can be found on the Boeing 787 Dreamliner. This 1 megawatt of electric power is used not for propulsion, but for ancillary functions, such as avionics, actuation, de-icing, cabin comfort. Electric power is distributed in low voltage in a hybrid DC-AC configuration, and it requires 500 kilometers of wiring and it weighs about 7.5 tons. How should we distribute power in an airplane or an aircraft? DC offers clearly a lot of advantages with respect to weight as well as efficiency, while there are challenges with DC distribution, and that would be in conversion and asset protection. As a matter of fact, medium voltage DC circuit breakers are currently lacking at any altitude, at sea level or at 10 kilometers. Also, at what voltage should we be distributing power? Given a power level, of course, going to higher voltages have an advantage in terms of reducing the cable size and cable weight, Also, it's more efficient to distribute power at higher voltages. Let's go through a back-of-the-envelope calculation for a concept plane, a special plane that's going to require 100 megawatts of electric power and distribute power at 500 or 1,000 volts. You can see that the copper diameter for the wires, just for the cabling, is going to be 6 to 8 inches in diameter. The cabling is going to weigh of the order of 100,000 kilograms. This is 100 tons. From a payload point of view, this is 1,000 passengers. From a gravimetric power density point of view, the 500 volt and the 1200 volt solutions are 1 to 2 kilowatts per kilogram. Clearly, these two solutions are not going to fly if we want to electrify a long-haul, wide-body aircraft. However, going to 10,000 volts allows us to shrink the diameter of the wire to 2 inches. The size of the weight of the cabling goes down less than 10 tons, 10,000 kilograms. The losses in the wiring will be of the order of kilowatts to possibly 10 kilowatts, as opposed to 100 kilowatts in the lower voltage cases. And the specific power is going to be approaching 20 kilowatts per kilogram for the cables. So now we have a shot possibly at flight. But going to 10,000 volts at 10 kilometers is a very challenging problem and has its own challenges. So at high altitude, the air pressure drops, and the electric field strength of gases also is lower at lower pressures. We can understand the electric field strength of gases as a function of pressure looking at the Paschen curves. So at very low pressures, there is very little gas to ionize or no gas to ionize, and in this case, the electric field strength asymptotically increases. At very high pressures, the carrier collisions don't allow for ionization, or they retard the ionization. In between these limits, electric field will cause ionization and avalanche multiplication, causing for the gas to break down. At 10 kilometers, the electric field strength of air is 1/3 of that at sea level. So the electric field strength goes down by a factor of 3 at 10 kilometers. At 20 kilometers, this is a 15 times reduction in the electric field strength. We have to watch for bubbles in liquids, voids in dielectrics. All of these are very susceptible to discharge events. And high-frequency switching, magnetic fields, temperature, and real-life geometries, they all reduce the electric field strength of the gas. So we can look at some of the partial discharge damage in these figures. You can see that the failures can be immediate, but more than likely, partial discharge damage is going to manifest itself over time. The figure at the top is showing partial discharge fail in switchgear, and the figure at the bottom on the right is looking at a printed circuit board over time as the damage is progressing. Possible solutions are superconducting wires, superconducting cables to replace copper. These solutions we know that can carry large amounts of current with good efficiency. However, the cryogenic systems to support the superconducting wire solution is going to be prohibitively heavy. Also, the reliability of cryogenic systems at altitude is questionable. On the insulation insulating materials. These materials need to be electrically insulating, however thermally conducting. We can't allow for voids. These materials have to be low in specific weight and be conformal. So, please consider this short, fast pitch as an informal request for information. We need your input, and thank you for your time and attention.
Thank you, Isik. Well, good afternoon, everyone. My name is Mike Haney. I'm a program director at ARPA-E. Well, you're all aware that we live in the age of digital computing, and that has had a huge impact on all of our lives. You may not be aware that before the age of digital computing, there was an era of analog computing. These computing machines were looked and operated quite differently than the digital machines you're most familiar with, yet they had a huge impact in the area of, for instance, the nuclear age, the space age. The analog computing techniques were subsumed about 60 years ago by digital computing, which never looked back, and pretty much universally all computing tasks now performed digitally. But as the title of this talk suggests, maybe it's time to take a look at some of the analog computing ideas again in the modern era. To be clear, we're talking about thinking about analog computing as accelerators for digital computers, maybe very efficient accelerators. So why would we do this? Why would we take a look at this? Well, it's really a confluence of several events here. ICT, information and communications technology, is the fastest growing energy consuming sector. And as this chart shows, it's only going to get worse. The demand for computing services is enormous and growing. Well, what's driving this is, if you may be aware, is a huge growth in machine learning and artificial intelligence, the IoT, Internet of Things, of course. The last summit, we talked about 20 billion items connected to the internet by 2020. Now the number I heard this morning was 50 billion items connected to the internet by 2020. Also, there's a concept called edge computing, where all the cloud computing will be offloaded, some of its computing, to the edge, closer to the user. Also, the scaling of silicon-based digital computing technology is coming to an end. We'll mention more about this in a second, due to physics regions. So, then there is a suggestion that analog computing can be very efficient, and so the question is, can this be transformative if we apply it properly? First, I want to step back a little bit into the so-called modern era of analog computing. First embodiments were mechanical. I particularly like this one here. It's a beautiful contraption. If you look carefully, you'll see pulleys and cables and gears and worm gears. Basically, these machines were used to implement directly a differential equation that described a system. This one could predict tides fairly accurately, about several hundred times faster than a person with pencil and paper. It was a very, very important tool. Of course, the age of electronics brought electronic embodiments. Here's a typical example of one used for the X-15 simulator, and if you look carefully, you'll see a patch panel where multiple operational amplifiers are connected together in the appropriate way to implement directly that differential equation. Well, as I said, about 60 years ago, analog computers went away. So what happened? Well, as I said, digital computing took over. For about 50 years of scaling of what's often termed Moore's law for silicon scaling. There are several ways of expressing Moore's law. The way I'm using here is 2 times improvement in compute operations per joule every 1.5 years. Very powerful law. I have my own personal example of analog computing. Some work that came out of my original research was we proposed to DARPA in about 1990 timeframe. It was a tabletop optical computer for a certain kind of imaging radar. The program was called Rapid SAR. At the time, we made a very strong case that the 100 watts we needed to do that computation was very, very favorably comparable example, to the digital equivalent, 10 kilowatts, in fact, of three racks of equipment were needed to make that happen. 100 times more efficient. Sounds pretty good. Well, apply Moore's law for 10 years, which is an order of magnitude every 5 years, and in just 10 years now, a digital computer could essentially be equivalent to that analog computer that I was talking about. So, the demise of analog computing was pretty thorough. But now let's fast forward 20 years later to the present day. And what do we have? It's kind of a busy chart, but it's plotting the efficiency of computation in joules per multiply and accumulate operation versus a timeline. And we're sitting over here on the right side of this chart. And there's a lot of details here, but just look at the trends, focus on the trends. The dashed red line represents Moore's law. And you can see that Moore's law was effective until about 2005, and then it began to tail off. And even after Moore's law, there was still some efficiency scaling, but now we're at a point of saturation of the efficiency, energy efficiency, and this is due to fundamental physics. The gates of the silicon are now approaching essentially atomic limits of performance. So why might we think about analog computers? Well, artificial neural nets might be the opportunity here. Of course, it's the key part of artificial intelligence now and the surge in machine learning. There's a cartoon of what an analog computer presently looks like. It's a multi-layer device consisting of an input plane and output plane of nodes and hidden layers, highly connected in a way that many, many multiply and accumulates are needed to compute the different weights of those interconnections in the learning phase. Very compute intensive, but very appropriate for many, many things. Right now, there's a surge in machine learning as we're talking about. It's currently based on digital hardware, but what if we could do it in the analog domain? Well, we are all walking around with an existence proof that neural nets can be efficient. Our brains operate on about 20 watts of power. It's not quite a fair comparison of ops versus flops, floating point operations, but nevertheless, to a rough order of magnitude, we can claim that our brains on a multiply and accumulate basis are about 1 million times more efficient than the digital silicon equivalent. So what's driving our interest, of course, is the rapid increase in machine learning and AI workloads. This chart is fascinating. It's just about a 6-year timeline showing the net increase in the vertical axis of the number of operations dedicated to machine learning. A 300,000x increase in just 6 years. For reference, I put Moore's law on there, even though it's not appropriate. Moore's law, which is a fantastic exponential growth, but machine learning is growing at a far higher exponential rate. Almost frightening, to be clear. So, does the end of Moore's law mean we have an opportunity for artificial neural nets, analog computing? Well, there are some clues that maybe this is happening. In the electronic world, there's some early analysis here shown in the chart on the right on the energy per multiply and accumulate being maybe 1 or 2 orders of magnitude more efficient than the equivalent digital artificial neural nets. So that may be encouraging, bears more analysis, of course. On the bottom panels, you'll see there might even be some integrated photonic, integrated optical techniques that can be brought to bear for artificial neural nets that would be much, much better than the bulk optical ones that people like me worked on in 1990. So let me wrap up with a list of questions. You're aware that at ARPA-E, when we begin thinking about possible areas to focus on, we like to do what's called a deep dive. Well, the beginning of that deep dive is to figure out what questions to ask and then to ask the questions. So let me give you a list of questions. So what are the limits of an energy per operation? Sort of a physics question. We should really narrow that down to see what the real opportunity could be, at least in principle. If we have that, can we efficiently exploit analog computing's inherent lower precision? That might be an opportunity, actually. How and where could we do that? And if we can do that, what would be the technical challenges we need to overcome? That's a hard question to answer, actually, easy one to ask. And if we could figure out which technical challenge to tackle, what would be the impact? So how much of the computation could we offload, for instance, in high-performance computing systems now at 10 gigaflops per watt? Could we impact there, and for which workloads in high-performance computing? In data centers, for what's now we're thinking AI and machine learning and deep learning, but are there more general applications we consider? I think that's an interesting question to ask. So I will finish up by putting all of these in sort of one succinct question, and that is it time for a deep dive into deep learning? And I will, with that, thank you for your attention, and I look forward to your ideas. I will be around as well. Come find me or contact us. I really look forward to hearing your ideas. If those weren't the right questions, please tell us which ones were. We'd like to know more. Thank you. So I'll now turn it over to Vicki for the Q&A.
Yeah, okay, well, awesome. So we have about 9 minutes or so to answer some questions, and apologies if we don't get to your questions. Please come engage with us after this session. We'll be outside. But for Kory, we have the question, renewables are zero-cost units, so why not take as much energy as possible from these resources?
So yes, renewables have a zero marginal cost. They really don't have much of an operating cost, but the point is that does not mean they have a zero marginal risk. When you have an intermittent resource like that and you push it onto the system, somebody has to be behind it, backing it up, and that costs money. And so when you ignore that, you have an inefficient outcome and you expose yourself to added risk that you don't need to do.
Great. So for Chris, we have the question, should we reduce VMT or reduce the energy consumption per mile?
That's a very good question. Clearly, the total energy consumed by the vehicle fleet is the product of the two. Reducing either VMT or reducing the energy intensity in terms of energy used per mile traveled, both of those are equally good. The problem with VMT and reducing VMT is that it's very closely linked to economic activity. Typically, the higher the economic activity, the higher the VMT. Increasing vehicle ridership from the 1.67 average in the United States higher than that, improving that, would obviously reduce overall VMT. That would probably require economic incentives and or policy and or regulation. So ignoring that for the moment, because we're a technology-based agency, it's equally good to have technologies that can both reduce VMT and reduce the energy intensity in terms of energy consumed per mile travel.
Great. So for Mike, we have the question, can quantum computing play a role?
Quantum computing. Well, it's a very intriguing question, and I don't know a whole lot about it, but people have begun to look into what's called quantum neural computing, artificial quantum neural computing. In fact, I just learned that whereas in digital quantum you have the qubit, in quantum neural computing you have something called the qron. You probably haven't heard that term, but it may become to the fore. But I think there's a lot to be done yet in the quantum computing world to see if it applies to neural computing. There's some understanding or some suggestion that some of the fuzzy logic concepts that might be inherent in quantum computing might be appropriate. So I believe it's an exciting area to watch.
Great. So for Isik, we have the question, since we don't have batteries yet, do we need to worry about distribution in long-haul aircraft?
Yeah, so there are at least 3-4 components for it to come together for all of these things to work. So my vision of all-electric long-haul aircraft is at least 30 years out. So we have to work on all of these components. The one that I'd like to focus on is the distribution, solve all those problems, and that will allow us to broaden the design space in the future. So to me, what's important is to broaden the design space, and then there will be other solutions for storage that other program directors are already thinking about.
Well, regarding storage, Kory, how does storage impact the renewables impact on the grid?
So storage will play a critical role in the future of the grid, but you have to keep in mind that you can bet on storage solving all of the problems, or you can bring forward to this challenge storage as a solution, as well as other solutions like changing the way that we operate the grid. And as you change the way you operate the grid, you'll extract more value out of the storage that you would already invest, meaning that you will need less storage to achieve the same goal. And so it's through a combination of the two that you want to go after innovating in the grid space.
Going back to Mike, regarding deep learning, why wouldn't regular industry invest in this direction? Where's ARPA-E's role?
Why? I'm sorry.
Regarding deep learning, why wouldn't regular industry invest in this direction? Where's ARPA-E's role?
I see. This is a universal question we have at ARPA-E. It's defining what our role is. Our role is obviously to sort of pan for the gold, look for the transformative opportunities that could be rapidly brought to bear. So I think it might end up being a mix. Machine learning is aggressively being pursued in industry. There is some academic work in analog. I think it'll end up being some combination, frankly.
So question for me, what is the total percentage of carbon removal / sequestration that we could reasonably achieve through afforestation? That is a good question, and that is the topic of numerous journal articles and a lot of modeling that's currently being done. I would say right now, within the US, our current forests can remove about 14% of emissions, and that's not even considering, how afforestation plays into this. So I don't exactly have a concrete number to give, but something that we should talk about outside of this. So a question for Chris. Why are you so sure that future automated vehicles will not be electric? Won't the irritation of long charging times be eliminated?
I think I did say in my presentation that in the far future, ultimately, we're pretty sure that there will be full electrification. So how far is the far future? We're not entirely sure, obviously, but it'll probably be decades hence. There's clearly some penetration of electric vehicles, fully electric vehicles today. It's at depending on where you are, whether you're in California or in the rest of the United States, it's less than 2% and increasing at a modest rate. In terms of hybrid vehicles, the hybrid vehicle penetration is substantially higher, of the order of 3 to 4 or 5%, depending on the specific vehicle class and the specific region. So our vision is that there will be significant increases in vehicle hybridization on the one hand, and then ultimately significant increases in the penetration of fully electric vehicles. And of course, many people have posited that autonomous vehicles, or AVs and EVs, go hand in hand. But it's worth noting that today, the vehicles that the 60 to 70 companies that are presently researching AVs, the vast majority of those are either hybrids or plug-in hybrids. One major reason is that the onboard power and computation requirements are so high that using an EV reduces their range enormously. So again, we do see full vehicle electrification as a very compelling long-term trend, but in the interim, we stand to consume an enormous amount of liquid fuels that we would like to minimize through the application of next car-like technologies to L4 and L5 AVs.
Great, so another question for Isik. Should we distribute the locations of energy storage on an electric airplane to reduce the requirements for electricity distribution?
Yeah, so in the calculations, we made certain assumptions where the storage would be and where the motors would be. And of course, we're coming back to the same question. All of these parts have to be designed all in holistically together, and it's very hard for me to predict what that design is going to look like. But clearly, the layout of the aircraft is going to be key. But what that looks like is going to be determined by all these other things where we have to look at the size of the weight of the cables, a whole bunch of other things along these lines. So it's very hard to predict what the layout of this plane is going to be.
All right. right, so I actually think that our time is up for this session, but I want to thank all of you for all of your great questions and all of you for the great fast pitches. So thank you so much.